Welcome! Today, we'll be tackling LeetCode problem number 1129, shortest path with alternating colors. This problem challenges us to find the shortest path in a graph where edges alternate between two colors. We'll explore the problem, break it down step by step, and discuss an efficient approach to solve it. Let's dive in. In this problem, you're given a graph consisting of n nodes, labeled from 0 to n1. The edges in the graph are categorized into two types, red and blue. These edges are represented by two separate lists, red edges and blue edges. For each pair, A, B, in red edges, there is a directed red edge from node A to node B. Similarly, for each pair, U, V, in blue edges, there is a directed blue edge from node U to node V. Your task is to determine the shortest path from node 0 to every other node, such that the sequence of edges along the path alternates in color between red and blue. The result should be an array answer of length n, where answer is x, represents the length of the shortest alternating path to node x. If no such path exists, the value for that node should be -1. The input includes the integer n for the number of nodes, the red edges array, and the blue edges array. The output is a list of integers representing the shortest alternating path lengths for all nodes. To better understand the problem, let's go through a few examples. In the first example, the graph has three nodes, and there are two red edges, one from node 0 to node 1 and another from node 1 to node 2. There are no blue edges in this case. The output is 0, 1, -1. Here's why: the distance to node 0 is 0 since it is the starting point. To reach node 1, you can take the red edge from 0 to 1, which gives a path length of 1. However, there is no valid alternating path to node 2 because there are no blue edges to continue from node 1. Therefore, the distance to node 2 is -1, indicating it's not reachable. In the next example, the graph again has three nodes, but this time there is one red edge from node 0 to node 1 and one blue edge from node 2 to node 1. The output here is also 0, 1, -1. The reasoning is as follows: the distance to node 0 remains 0. To reach node 1, you can take the red edge from 0 to 1, resulting in a path length of 1. However, node 2 cannot be reached from node 0 using a valid alternating sequence of edges. Even though there is a blue edge ending at node 1, it does not connect from node 0 or form part of a valid alternating path. Thus, the distance to node 2 is -1. Now consider a third example where the graph has three nodes, with a red edge from 0 to 1 and a blue edge from 1 to 2. The output is 0, 1, 2. Here's the reasoning: the distance to node 0 is 0. To reach node 1, you can take the red edge from 0 to 1, which gives a path length of 1. To reach node 2, you can take the red edge from 0 to 1 and then the blue edge from 1 to 2. This forms a valid alternating path, and the total path length is 2. This example demonstrates how alternating sequences of edges allow us to reach all nodes in the graph, provided such paths exist. Finally, keep in mind the constraints: the number of nodes can be up to 100, and the total number of edges, both red and blue, can be up to 400. The solution needs to work efficiently within these bounds. There are several edge cases to consider in this problem. First, if both red edges and blue edges are empty, the output will be 0, -1, -1, because only the starting node 0 is reachable. Second, if there is only one node, meaning n equals 1, the output will always be 0, since there are no other nodes to reach. Third, in a disconnected graph where certain nodes cannot be reached via valid alternating paths, those nodes will have a value of -1 in the output. Fourth, remember that paths must alternate between red and blue edges. A sequence of edges that does not alternate is considered invalid. Finally, for larger input sizes, the solution must be optimized to handle up to 100 nodes and 400 edges efficiently. This ensures the algorithm performs well even in the upper bounds of the constraints. To solve this problem, one approach we might initially consider is using a brute force breadth first search, or BFS, since BFS is a natural fit for finding the shortest path in a graph. In this approach, we would treat the graph as a normal directed graph and attempt to find paths from the start node to all other nodes. However, the key challenge here is that the problem requires paths to alternate between red and blue edges. If we use this brute force method and ignore the colors of the edges, it could lead to invalid solutions. For example, the algorithm might traverse two consecutive red edges, which would violate the requirement for alternating edge colors. While the time complexity for this approach is O, n plus e, where n is the number of nodes and e is the total number of edges, it fails to satisfy the problem constraints. Therefore, this unoptimized BFS approach is not sufficient for solving the problem as given. To address the issue of alternating edge colors, we can turn to an optimized BFS approach that is color-aware. The key intuition behind this approach is to modify BFS so that it maintains separate states for paths ending in red and blue edges. This means that for each node in the graph, we keep track of two distances, one for paths that end with a red edge and one for paths that end with a blue edge. The graph can essentially be thought of as two overlapping subgraphs, one for red edges and one for blue edges, with color alternation represented as transitions between these layers. The process works as follows. Starting from node 0, we initialize two separate queues, one for red edges and one for blue edges. We use a 2D array dist node, color, to track distances, where the color indicates whether the path ends in red or blue. During traversal, we enforce the color alternation by ensuring that if the current path ends with a red edge, the next edge must be blue, and vice versa. We also ensure that no edge is revisited in the same context, meaning the same node and edge color combination. This approach guarantees that all valid paths are explored without redundancy. The time complexity remains O, n plus e, since each edge is processed at most twice, once for each color, making this approach both correct and efficient. The optimized BFS approach is the ideal strategy for this problem because it explicitly accounts for the requirement of alternating edge colors while leveraging the inherent properties of BFS to find the shortest path. Its efficiency lies in how it avoids redundant computations and ensures correctness by exploring only valid paths. However, there are some trade-offs to consider. This method requires additional memory to store the 2D dist array for tracking distances and to keep track of visited edges for both red and blue contexts. Nonetheless, this additional memory usage is a reasonable trade-off given the constraints and goals of the problem. Other alternatives, such as the brute force approach, were rejected due to their inability to handle color alternation, and DFS was dismissed because it is less suited for shortest path problems and would require extra effort to replicate BFS-like behavior. The key insight here is to view the problem as a layered graph, where transitions between red and blue subgraphs represent valid paths. By using the 2D dist array, we ensure that the first time a node is reached with the correct color alternation, it represents the shortest path. With a time complexity of O, n plus e, and a space complexity of O, n plus e, to handle the graph and auxiliary data structures, this approach achieves an optimal balance between efficiency and correctness. To solve the shortest path problem using an unoptimized BFS approach, we begin by representing the graph as an adjacency list. This allows us to efficiently store each node and its corresponding neighbors. While the graph may include additional constraints, such as edge colors or weights, we initially disregard these for simplicity in this brute force implementation. Next, we need to set up the necessary components for our BFS. A queue will be used to manage the nodes we explore, ensuring we process nodes level by level. Each entry in the queue consists of a node and the current path length to reach it. Additionally, a visited set is crucial to keep track of nodes we've already explored. This helps prevent revisiting nodes and ensures that the algorithm terminates as expected. For example, we might initialize the queue with the start node and a path length of 0, while simultaneously marking the start node as visited. This setup forms the foundation of the BFS traversal process. The BFS process begins with a loop that continues as long as the queue has nodes to process. In each iteration, we dequeue the first element from the queue to explore it. If the current node matches the target node, we immediately return the path length, as BFS guarantees this is the shortest path to the target. If it's not the target, we proceed to examine its neighbors. For each neighbor, we check if it has already been visited. If not, we mark it as visited to avoid revisiting it in the future and enqueue the neighbor with an increment path length. This process ensures that all nodes at the current level are fully explored before moving on to the next level. By maintaining this order, BFS guarantees an optimal solution for shortest path problems in unweighted graphs. The BFS algorithm terminates under two conditions: either the target node is found, in which case the path length is returned, or the queue becomes empty, meaning the target is unreachable from the start node. In the latter scenario, we return a special value, such as -1, to indicate this result. The output of the algorithm is simple, it's either the shortest path length or -1 if the target cannot be reached. BFS guarantees the shortest path due to its level-by-level exploration. The first time a node is reached, it's via the shortest path. From a complexity perspective, BFS requires linear space for both the queue and the visited set, leading to O(n) space complexity where n is the number of nodes. Time complexity is O(v plus e), where v is the number of vertices and e is the number of edges, since each node is processed once, and all its edges are explored. To implement BFS effectively, we rely on three key data structures. First, the queue is used to manage nodes in a FIFO order, ensuring that nodes are processed level by level. Second, the visited set keeps track of nodes already explored, preventing cycles and redundant work while ensuring the algorithm terminates correctly. Finally, the adjacency list provides a compact and efficient way to represent the graph, enabling quick access to a node's neighbors. It's also important to note how edge cases are handled. For example, in a disconnected graph, if the target node cannot be reached, the algorithm will correctly return -1, as the queue will eventually empty without finding the target. These components and considerations ensure the BFS algorithm is robust and efficient. In graphs with cycles, the visited set plays a critical role in preventing infinite loops by ensuring each node is processed only once. In the case of a single-node graph, where the start and target nodes are the same, the algorithm immediately returns a path length of 0. For large graphs, BFS handles the workload efficiently within its O(v plus e) complexity bounds, making it scalable for practical use cases. To visualize BFS, imagine the graph as a network of cities connected by roads. Starting from the source city, BFS explores all neighboring cities first, then expands outward level by level. The queue acts as a line of explorers waiting their turn to process each city, while the visited set ensures no city is revisited, even if multiple roads lead to it. This systematic approach guarantees an optimal pathfinding process in unweighted graphs. To solve the problem, we start by importing the necessary libraries deque and defaultdict from the Python collections module. These will help us manage the graph traversal and adjacency lists efficiently. Within our solution class, we define the function shortest alternating paths that receives the number of nodes n, along with the red and blue edges as input. The first step is to construct separate adjacency lists for the red and blue edges using defaultdict. This allows us to store the graph structure in a way that's easy to traverse based on edge color. Next, we define a distances list to keep track of the shortest distance to each node, where -1 indicates that the node has not yet been visited. For node 0, the starting point, we initialize both the red and blue distances to 0, as it takes no steps to reach itself. To perform the breadth-first search, BFS, we set up a queue that starts with two states for node 0, one assuming we arrived via a red edge and the other via a blue edge. Each state in the queue includes the current node, the color of the edge used to reach it, and the current distance traveled. As we process the queue, we determine the next graph and color to explore by alternating the edge color. This ensures the paths alternate correctly between red and blue edges. For each neighbor of the current node in the graph corresponding to the next edge color, we check if it has already been visited using that color. If not, we update the distance for that neighbor with the current distance +1 and add the neighbor to the queue for further exploration. This ensures that we only visit unvisited nodes and continue the BFS until all possible paths are explored. Once the BFS completes, we construct the result by combining the distances for red and blue paths to each node. If a node is unreachable by both red and blue edges, we append -1 to the result. If it's reachable by only one edge color, we take the distance for that color. Otherwise, we select the minimum of the two distances, as we're looking for the shortest path. Finally, the function returns the result list, which contains the shortest alternating path distances to all nodes in the graph. To solve the problem, we start by creating two separate adjacency lists to represent the red and blue edges. These lists will help us differentiate between the two types of edges in the graph. Using hash maps, we initialize the red graph and blue graph to store the connections for each node. For every node in the graph, we initialize an empty list in both maps to ensure all nodes are accounted for, even those without incoming or outgoing edges. Next, we populate the adjacency lists using the red and blue edge inputs. For each edge in red edges, we add its destination to the sources list in red graph, and we do the same for blue edges in blue graph. After setting up the graph structure, we initialize a 2D array distances to keep track of the shortest distances to each node. The array has two columns, one for distances reached via red edges and the other for blue edges. Initially, all distances are set to -1, indicating that no node has been visited yet. Now, we set the starting point for our traversal. The distance to node 0 using either a red or blue edge is set to 0 because we're already at the starting node. To perform the breadth first search, BFS, we initialize a queue where each entry contains the current node, the color of the last edge used, and the distance traveled so far. We start by adding two entries for node 0, one assuming the last edge was red and the other assuming it was blue. Then, we proceed with the BFS loop. For each node we dequeue, we determine the graph corresponding to the alternate color. For instance, if the current edge color is red, the next graph is blue graph, and vice versa. We then iterate through all neighbors in the alternate graph, checking if they have been visited with the current color. If not, we update their distance in the distances array and enqueue them along with the next color and the increment distance. This ensures that we explore paths alternately and systematically, minimizing the distance as we go. After completing the BFS traversal, we need to compile the results. For each node, we check the shortest distance reachable either via a red or blue edge. If both distances are -1, it means the node is unreachable, so we set its result to -1. If only one of the distances is -1, we use the valid distance. Otherwise, if both distances are valid, we take the minimum of the two. This logic ensures that the result array accurately represents the shortest path to each node with alternating edge colors. Finally, we return the result array, which contains the shortest alternating path distances for all nodes in the graph. Here, we start with a small graph consisting of 3 nodes and 2 types of edges, red and blue. The red edges connect node 0 to node 1 and node 1 to node 2, while there's a blue edge directly connecting node 0 to node 2. First, we construct the adjacency lists for both red and blue edges, which represent the graph. The red adjacency list shows that node 0 leads to node 1 and node 1 leads to node 2. The blue adjacency list only has node 0 leading to node 2. Next, we initialize the distances array. This array keeps track of the shortest path to each node, where distances i0 represents the shortest path via a red edge and distances i1 represents the shortest path via a blue edge. Initially, the distance to the starting node, node 0, is set to 0 for both red and blue edges, while all other nodes are set to -1, indicating they are not yet reachable. We also initialize the BFS queue with 2 entries, starting from node 0 using a red edge and starting from node 0 using a blue edge, both at a distance of 0. Now, we're ready to begin the BFS process to calculate the shortest paths. The BFS process begins by dequeuing the first element, which is node 0 using a red edge at a distance of 0. From here, we check the blue neighbors of node 0, which is node 2. Since node 2 has not been reached via a blue edge yet, we update its distance to 1 and enqueue it with the information that it was reached via a blue edge. Next, we dequeue the second element, which is node 0 using a blue edge at a distance of 0. From here, we check the red neighbors of node 0, which is node 1. Since node 1 has not been reached via a red edge yet, we update its distance to 1 and enqueue it with the information that it was reached via a red edge. Moving forward, we dequeue node 2 using a blue edge at a distance of 1. However, node 2 has no neighbors to visit, so no further updates are made. Finally, we dequeue node 1 using a red edge at a distance of 1. From here, we check the blue neighbors of node 1, which is node 2. Since node 2 has already been reached with a shorter distance via a blue edge, no update is made. This completes the BFS process for this example. To compute the final result, we take the minimum distance for each node between the two available options, red and blue edges. If a node is unreachable via both colors, the result for that node should remain -1. For this example, node 0 is the starting point and thus has a distance of 0. Node 1 is reachable via a red edge with a distance of 1. Node 2 is reachable via both red and blue edges, but the shortest path is via the blue edge with a distance of 1. Combining these distances gives us the result array 0, 1, 1. Moving to another example, we now analyze a disconnected graph with 4 nodes. The red edge connects node 0 to node 1, and the blue edge connects node 2 to node 3. First, we construct the adjacency lists. The red adjacency list shows node 0 leading to node 1, and the blue adjacency list shows node 2 leading to node 3. Next, we initialize the distances array to track the shortest paths for each node. Node 0 is the starting point, so its distances are set to 0 for both red and blue edges, while the other nodes are initialized as -1. The BFS queue is also initialized with node 0 using both red and blue edges at a distance of 0. In the first BFS iteration, we dequeue node 0 using a red edge at a distance of 0. From here, we check its blue neighbors, but there are none. In the second iteration, we dequeue node 0 using a blue edge at a distance of 0. From here, we check its red neighbors, which is node 1. Since node 1 has not been reached via a red edge yet, we update its distance to 1 and enqueue it with the information that it was reached via a red edge. In the third iteration, we dequeue node 1 using a red edge at a distance of 1. However, node 1 has no neighbors to visit, so no further updates are made. Finally, we calculate the result array. For this disconnected graph, we combine the distances to form the result. Node 0 is the starting point, so its distance remains 0. Node 1 is reachable via a red edge with a distance of 1. Nodes 2 and 3 are part of a separate component and are unreachable from node 0, so their distances remain -1. This gives us the final result array 0, 1, -1, -1. Now, let's consider an even simpler example, a single node graph. Here, there are no edges, so both the red and blue adjacency lists are empty. As there's only one node, we initialize the distances array with 0 for node 0 for both red and blue edges, indicating that it is the starting point. The BFS queue is initialized with node 0 using both red and blue edges at a distance of 0. In the first BFS iteration, we dequeue node 0 using a red edge at a distance of 0. Since there are no neighbors to visit, no updates are made. Similarly, in the second iteration, we dequeue node 0 using a blue edge at a distance of 0. Again, there are no neighbors to visit, so no updates are made. Finally, since this is a single node graph, the result array contains only one value, which is 0, representing the shortest path to itself. The final output for this example is 0. To analyze the time complexity of our solution, we start by looking at the graph construction phase. Here, we process the red and blue edges to build their respective adjacency lists. Since each edge is visited exactly once during this process, the time required is proportional to the number of edges, which is O, R plus B, where R represents the red edges and B represents the blue edges. Next, we consider the BFS traversal. In this step, the algorithm explores the graph level by level, starting from node 0. For each node, it processes all its neighbors from either the red or blue adjacency list, depending on the color of the incoming edge. Importantly, since each edge is processed only once per color during the traversal, the BFS phase also takes O, R plus B, time. This ensures that we are efficiently exploring the graph without redundant work. Now, after the BFS traversal is complete, we need to combine the results to produce the final output. This involves iterating through the distances array to construct the result array, where we determine the shortest path to each node. Since this operation requires visiting each node once, it takes O, n, time, where n is the number of nodes in the graph. When we add up the time complexities of all the steps, graph construction, BFS traversal, and result computation, the overall time complexity becomes O, R plus B plus n. This reflects the fact that we process all edges and nodes efficiently. However, in the worst-case scenario, when the graph is densely connected with O, n squared, edges, the time complexity grows to O, n squared, as the number of edges dominates the computation. Let's now examine the space complexity of the solution. First, we consider the adjacency lists for the red and blue graphs, which store all the edges. The space required for this is proportional to the total number of edges, O, R plus B. Next, we have the distances array, which keeps track of the shortest distance to each node for both red and blue paths. Since this array needs to store two values for each node, its size is O, 2*n, which simplifies to O, n. Lastly, during the BFS traversal, the queue data structure is used to store nodes waiting to be processed. In the worst case, the queue can hold all nodes in the graph at once, resulting in a space requirement of O, n. Adding up these components, the overall space complexity of the solution is O, R plus B plus N, with contributions from the adjacency lists, the distances array, and the BFS queue. When we compare this with a brute force approach, the difference becomes evident. A naive method might involve exploring all possible paths from the starting node to every other node, which would result in exponential time complexity due to the sheer number of possible paths in a graph. By contrast, the optimized BFS approach evaluates each node and edge at most once, achieving a linear time complexity of O, R plus B plus N. This makes our solution both computationally efficient and practical for large graphs. Finally, let's break down the best, average, and worst-case scenarios for the algorithm. In the best case, where there are no edges in the graph, the BFS terminates immediately after checking the nodes, resulting in O, N, time and space. For the average case, in a sparse graph with relatively few edges, the time complexity remains O, N plus or plus B, as the number of edges is small compared to the number of nodes. In the worst case, when the graph is densely connected with O, N squared, edges, the time complexity increases to O, N squared, because of the high edge count. Mathematically, the big O complexity of BFS is derived from the fact that it processes each node and edge exactly once. This ensures that the total time required is proportional to the sum of nodes and edges, O, R plus B plus N. Similarly, the space complexity is dominated by the adjacency lists and BFSQ, both of which scale linearly with the size of the graph. This guarantees an overall space complexity of O, R plus B plus N, making the solution efficient even as the graph scales. When solving this problem, there are several common mistakes to watch out for. First, failing to consider edge cases like an empty graph or a graph with just one node can lead to runtime errors or incorrect outputs. It's crucial to test your solution on minimal or special inputs to ensure it handles all scenarios properly. Next, inefficient graph traversal, such as using unoptimized BFS or DFS without pruning, can lead to excessive computations and even time limit exceeded errors on larger graphs. To prevent this, use visited sets to avoid revisiting nodes and terminate early once the shortest path is found. Another mistake is not handling weighted edges correctly. Assuming all edges have equal weights may work for unweighted graphs, but for weighted graphs, algorithms like Dijkstra's or Bellman-Ford are needed to account for the weights. Lastly, ignoring directionality in directed graphs can result in invalid paths being included. Always respect edge directionality during traversal to ensure correctness. Overcomplicating the implementation is another pitfall to avoid. Adding unnecessary checks, data structures, or overly verbose code can make your solution harder to debug and less clear. Instead, aim for a clean, modular approach and optimize only if there's a measurable performance problem. From an interview perspective, clarity should always be your top priority in the first pass. Interviewers generally prefer a correct and clear solution over an overly complex one, even if it's optimized. For example, starting with a simple BFS implementation is often a good strategy before introducing more advanced techniques. Also, be prepared to work with different graph representations, like adjacency lists or matrices, as interviewers may specify a particular format. Discussing trade-offs between approaches, such as BFS versus Dijkstra, shows a deeper understanding of the problem. And finally, after coding, take the time to discuss edge cases with your interviewer to demonstrate thoroughness and attention to detail. This problem shares similarities with several other graph-related challenges that you might encounter. For instance, LeetCode 200, number of islands, involves BFS or DFS traversal to count connected components, making it conceptually similar. LeetCode 127, word ladder, is another shortest path problem but in the context of an unweighted graph. Then there's LeetCode 743, network delay time, which focuses on weighted graph traversal and often requires Dijkstra's algorithm for an efficient solution. Finally, LeetCode 133, clone graph, is about graph traversal and reconstruction, which also involves BFS or DFS. Exploring these related problems can help you strengthen your understanding of different traversal techniques and their applications. Beyond the standard approaches, there are alternative methods you can consider depending on the problem constraints. Dijkstra's algorithm, for example, is more efficient than BFS for weighted graphs but requires additional data structures like a priority queue, with a time complexity of O, V plus E, asterisk log, V. A asterisk search algorithm builds on this by incorporating heuristics, which can make it faster, but you need to carefully design admissible heuristics for it to work effectively. Dynamic programming approaches like Floyd-Warshall handle all pairs shortest paths but are computationally expensive, with a time complexity of O(v cubed, making them impractical for large graphs. Finally, bidirectional BFS can significantly reduce the search space for unweighted graphs by working from both the source and target simultaneously, though it does require extra memory for maintaining two queues and visited sets. Each of these methods has its trade-offs, so choosing the right one depends on the specific requirements and constraints of the problem. Great job on completing this walkthrough. To summarize, this problem showcases the power of BFS in exploring constrained shortest path problems. Remember to practice problems like this to strengthen your graph traversal skills. Thanks for watching, and be sure to subscribe for even more algorithm insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!